Hi everyone. In today's video, we'll talk about the BigO notation. So the purpose of BigO notation is to find how your running time changes with the size of the input. So it's easier to explain this with an example. Suppose I have an algorithm where for an input size of 1, it takes 1 second to run. For an input size of 2, 2 seconds to run. Input size of 3, 3 seconds to run. So if I plot a graph of this, you can see the running time increases linearly with the size of the input. Let me explain with another example. Suppose I have another algorithm where for one size input 1, it takes 1 second. For size input 2, takes 4 seconds. Size 3, 9 seconds. So basically n square, where n is the size of the input. So if you plot a graph of this, your graph will look something like this. So this is called a quadratic algorithm. So mainly what you're trying to see is how does the running time change as your input size keeps increasing. So this was a layman way of looking at it. Let's look at a little bit more mathematically precise definition. So mathematically, as n is the size of the input, so as n tends to infinity, if the t of n is the actual running time, if the actual running time is less than or equal to a constant times your approximation, then your actual running time is said to be in BigO of that approximation. So what we mean by this? Suppose, okay, I have a code which is like this. Say something like this. So we know it's linear and we know even for 0 it's 2. Say suppose the actual running time is 2 plus the size of the input. Okay, so for 0 it will take 2 seconds. For 1 it will take 3 seconds. For 2 it will take 4 seconds, and so on and so forth. So 2 plus size of input. Suppose that is my actual running time, which is t of n. Now for me to say, I want to denote it in terms of BigO. So BigO, like I said earlier, is an approximation. It's not an exact. So if I want to denote it in terms of BigO, if this condition is true, then my BigO is true. So some constant times this, as n tends to infinity, should be bigger than the actual running time. So suppose my approximation function is 10 times n. Okay, so for n equal to 0, of course it's not bigger than it. It should be bigger, but for n equal to 0 is not bigger, but I care for that as n tends to infinity. So let's see again for the next value. For 1, 10n will be 10. For 2, 10n will be 20. So the approximation I came up with as n tends to infinity is going to be above this line, which is the actual function. So in that case, I can say my function is in BigO of n. So this constant does not matter. You can pick whatever constant in this you want. But when you talk about BigO, this constant doesn't matter. You can just pick any arbitrarily big constant you want. If this as long as constant times this takes more than the actual running time as n tends to infinity, your approximation is correct. So this is why we call this an upper bound. So BigO means my code runs in this time or faster as n tends to infinity. So it's an upper bound. So one caveat here. Since I said it has to be that or faster, suppose this is the actual running time of my code. Okay, n. N is the actual running time of my code. N is the size of the input. I can also say my code runs in BigO of n square. Why is that? That is because it has to be this or faster, the actual running time. As long as my approximation is slower than the actual running time as n tends to infinity, my approximation is good enough. So theoretically, I can say this code is in BigO of n square. But then in an interview, if you say that this is BigO of n square, they will fail you because usually when they say BigO, they want a tighter bound, the tightest bound of the upper bound. So you cannot say this is in BigO of n square. You have to say it's in BigO of n. So now that's out of the way. What's next? So next, we've covered this. We covered the mathematical part. So mathematical, just to reiterate, you can say your function, your running time is in BigO of n if this times a constant is more than the actual time taken. T of n is the actual time. So the actual time taken should be less, or other, to look at the other way, your approximation to take more time than the actual time, then this approximation is correct. And that is as n tends to infinity. So for lower values of n, that may not be true, but as n tends to infinity, c times that approximation takes more time than the actual running time. Now let's look at a few examples, real examples of BigO of n. Now say, let's look at algorithm that takes constant time, BigO of n time. Before we see BigO of n, there is also something called BigO of 1. BigO of 1 means it's constant time. An example of this would be, suppose you want the first element in an array. Say you want whatever array is given, you want the zeroth index of that array. Not, it doesn't matter how big your array is. If you want to pick the first item, or the element at the 0 index, it's always going to take the same time regardless of the size of the array. So a function like that is called a constant time, where the time taken does not change with the size of the input. Now let's look at BigO of n. So BigO of an n would be, suppose you have an array 1, 6, 8, 12, 15. If your code goes through every single item and prints it out, that will be BigO of n, because the time taken is proportional to the number of elements. So another way to look at it, BigO of n would mean you have to do n number of operations, n being the size of the input. So if you have to print every item, so printing an item is an operation, you have to do it n times. So if you have 50 items, you have to print 50 times, 60 items, 60 times. So that's how you would say this is a BigO of n. Now let's look at an algorithm that does BigO of log n. Suppose you have an array. Now, suppose your algorithm divides it by half and then takes the left half and again divides it by half, takes the left half and keeps on dividing it by half until you're left with one item. So now, in BigO, like I said earlier, you have to see how your running time, or another way to look at it is number of operations relate to the size of the input. So suppose I have n items in an array and I want to keep dividing it by half until I reach one item. So how many operations would I have to do? I have to do n divided by 2 first operation, second operation will be again by 2, third operation will be again by 2, and I keep dividing by 2 until I reach one item. So what this would mean is, if I keep on dividing by 2, suppose I have to divide it x times. So n divided by, so if you divide by 2, divide by 2, divide by 2, it's x times will be n divided by 2 raised to x equal to 1. Let me write it more clearly. N divided by 2 raised to x equal to 1, which means 2 raised to x equal to n, which means x is log of n to base 2. So x is the number of times I'm dividing by 2, which is the number of operations. So number of operations, I want to tie it to the size of the input, which is n. So number of operation is log of n. So that's why I would say this is BigO of log n. So always you have to remember is you have to see, you can define operations in different way, but the way to look at it is number of operations, this thing's relation to the size of input. That's how you always find out what's the BigO. So if you, like we saw earlier, when we divide by half, the number of operations you have to do for say input size n is log of n, because that's the number of times you divide. When you divide by 2 to reach 1, it's log of n. So if you have an array of size say 100, if you take log of 100, that's the number of times you can divide it by 2 to reach one element. So that has a complexity of log n. So let's look at another example, BigO of n square. So suppose you have a code that does this. For I equal to 1, I less than equal to n. N is say a number you passed to your function. Say for I equal to 1, I less than equal to n, I plus plus, j equal to 1, j less than equal to n, j plus plus. So here what happens? So if you have, say, you pass in 5. So your outer loop will run 5 times, and for every time the outer loop runs, this will run 5 times. So what does that mean? When I equal to 1, this will run, inner loop will run 5 times. When I equal to 2, inner loop will run 5 times. I equal to 3, 5 times. 4, inner loop 5 times. 5, inner loop 5 times. So you have to run 5 plus 5 plus 5 dot 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 till 5 times, like 5 times altogether. This altogether it's 5 times, right? So which is basically 5 times 5. Or say, now suppose we are doing n. Instead of 5, say this is, if you just take it as n, basically for I equal to 1, inner loop will run n times. I equal to 2, inner loop will run n times. Dot 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 till I equal to n times. So basically the total number of times this run, or the total number of operations. Suppose you're doing something here, that is your operation. So the total time you're doing this operation is n plus n plus n, like n times, so which is n times n, which is n square. So this is the program that you will say runs in BigO of n square, because the number of operations is n square times the input size. So input is n, you have to do n square operations. So we are tying the number of operations to the size of input. Now let's look at another example. Say BigO of 2 raised to n. So for 2 raised to n, it's a little bit more tricky to understand. So let's take an example of Fibonacci series without using memoization. So, and also using recursion. So let me give an example. So this is how the Fibonacci series is 0, 1, 1, 2, 3. So basically you take these two, add it, that's the next number. So if you say this is the index 0, 1, 2, 3, 4. So if this is the index. So at element 0 it's 0, at index 1 it's 1, at index 2 it's index 1 plus index 0, index 3 is index 2 plus index 1. So if you write code for this using recursion, it will be something like so basically in this code, if I'm saying I equal to 0, which is I is the index. If index is 0, return 0. If index is 1, return 1. Else return fib of I minus 1 plus fib of I minus 2. So for this one, fib of I minus 1 is 1. Fib of I minus 2 is 0. So fib of 2 is fib of 1 plus fib of 0, which is 1 plus 0, which is 1. So how do you analyze the time complexity? So like I said, you want to relate the size of input to the number of operations. So in this case, let's see how we do that. So again here, we are not using memoization. Memoization is where you store the previous result to reduce the number of operations. Suppose we are not doing that. So say, let's take an example. So I'll take one more here, 5. 5 is 3 plus 2, 5, yeah. So this is the index and this is the Fibonacci of that. So if I have to calculate 5, okay, Fibonacci of 5, I will have to calculate Fibonacci of 4 and Fibonacci of 3, right? Because Fibonacci of 5 is Fibonacci of 4 plus Fibonacci of 3. Now to calculate Fibonacci of 4, I'll have to calculate Fibonacci of 3 and Fibonacci of 2, because Fibonacci of 4 is Fibonacci of 3 plus Fibonacci of 2. To calculate Fibonacci of 3, I'll have to calculate Fibonacci of 2 and Fibonacci of 1. To calculate of 2, I'll have to calculate Fibonacci of 1 and Fibonacci of 0. So 1 is already, we know the answer. Again for 2, it is 1 and 0. For 3 again, Fibonacci of 2 plus Fibonacci of 1. For 2, it is Fibonacci of 1 plus Fibonacci of 0. And for the 3 and 2 and 1. So here, an observation to make is, suppose I'm counting the depth from here. So for the top one, depth equal to 0. Here, depth is equal to 1. Here, depth equal to 2. Here, depth equal to 3. And here, depth equal to 4. So if you take for any of these Fibonacci, you will notice the maximum of depth it reaches is that number minus 1. That's the max. So this is like say 1, 2, 3, 4. Number index, this is the index, that minus 1 is the maximum depth we are going to. So let me write that down. And we'll see another example of how that is true. So this is my claim. The max depth is index minus 1. So let's say another example. Index 2. So I'm saying for index 2, the max depth will be 1. Let's try. For 2, the Fibonacci is Fibonacci of 1 plus Fibonacci of 0. So you see the max depth here, depth is 0, depth equal to 1. And what I claimed is max depth is index minus 1. So 2 minus 1 is 1 and max depth is 1. Let's see one more example. Say for index 3. For index 3, I am claiming max depth will be 2 because index minus 1. Let's see. For 3, you'll have to calculate Fibonacci of 2 and Fibonacci of 1. And then for 2, it's again Fibonacci of 1 and Fibonacci of 0. So here the depth is 0, 1, 2. So 2 is your depth, max depth, which is what I said. So now that we have established max depth is index minus 1, now we're making an approximation here going forward. So the approximation is, I'm going to assume that the tree is a full tree. So for 5 we saw it only came till here, but I'm going to assume it's like a full tree like this. So this is a full tree. So if the tree is full, the analysis is a little easier. That's why I want to say a full tree. So if the tree is full, what I want to know, so every single node is an operation, right? Because say if I was calculating Fibonacci of 5, I had to do first 4 and then 3. For 4 I have to do 3 and 2. So every single node is an operation. So now if I can find how much are the total number of nodes, so if I find total number of nodes and find its relation to the input size, which is the index. Here the index is the input size. If I can find a relation between these two, pretty much my job is done. So one approximation, like I said, we have made is we are assuming a full tree. So say for 3, if I'm doing 2, 1 and for 2, 1, 0. So this doesn't have children, but for our approximation, we are going to assume this also has children, some children. And that is fine because like I said, BigO is an upper bound. So here we will be overestimating the amount of operations. So now let's see how do I find the total number of, the relation between total number of nodes and index. So first level, the depth 0, total number of nodes is 2 raised to 0, which is 1. Here the number of nodes is 2 raised to 1, which is 2. Here number of nodes is 2 raised to 2, which is 4. So the total number of nodes in a tree is 2 raised to 0 plus 2 raised to 1 plus 2 raised to 2 plus dot 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 2 raised to whatever the depth is. Now we already know the depth is index minus 1. So which means the total number of nodes is 2 raised to 0 plus 2 raised to 1 plus 2 raised to 2 plus dot 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 2 raised to index minus 1. Okay, so this is the total number of nodes. So this is the total number of nodes. So I'm going to write this down separately. 2 raised to 0 plus 2 raised to 1 dot 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 till 2 raised to index minus 1. Again, remember, total number of nodes is pretty much the total number of operations. I can write it down here, operations is 2 raised to 0 plus 2 raised to 1 plus dot 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 plus 2 raised to index minus 1. Now we need to find this one. Now to find this, there is something called a geometric series. So this you can look it up on Google. So basically what geometric series says is a plus ar plus ar square plus ar cube plus dot 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 plus a into r raised to n minus 1 is equal to a into 1 minus r raised to n over 1 minus r. So this is the formula for a geometric series, which is similar to this one. So here for us, a is equal to 1, r is equal to 2, and n minus 1 is equal to index minus 1, which means n is our index here. I mean, n not the size of input. Remember, right now I'm saying about this geometric series expression here. So in this expression, n is our index, because n minus 1 is index minus 1. So now if I substitute it in this equation, it will become a is 1 into 1 minus r raised to n, 1 minus 2 raised to index over 1 minus r, 1 minus 2, 1 minus 2 raised to n over 1 minus 2, which is, this is the total number of nodes. So let me write that here. Total number of nodes one into 1 minus 2 raised to index over 1 minus 2. This is my total number of operations. So which means my total number of operations is 2 raised to index minus 1 over 2 minus 1, which is 2 raised to index minus 1 over 1. So as an approximation, so basically here what I'm saying is this is equal to 2 raised to the index. Index is the size of the input to this program, minus 1, which is approximately 2 raised to index. Index is the input to the Fibonacci program, which is, and if you say the size of the input is n, it is 2 raised to n. So that is how you get 2 raised to n. And you can extrapolate this. So if you have, say, if you have some recursive function that takes 3 paths, so instead of 2, it will be, so here you will have total number of nodes 3 raised to 0. Here 3 raised to 1, and then again if all of them have 3 kids, 3 raised to 2. So you can just follow whatever I did in the previous one, and you can derive for that also, and this will ultimately come out to 3 raised to n. So basically, for any recursive function, how many branches you have, that raised to the size of the input is your time complexity. So usually in interviews, they will not just ask for time complexity, they'll also ask for space complexity. But in this video, to keep it simple, I'll just cover the time complexity. So these are the general complexities of programs or algorithms that you will come across. Constant time, log of n, log square n, square root n, n log n square, so forth, and 2 raised to n will be somewhere there. So all of those on that side are slow, this is fast. But generally, like I drew a red line here, anything n log n or faster is considered to be an efficient algorithm. If your algorithm is n square or more, generally that's considered to be an inefficient algorithm. In certain cases, it's not possible to avoid it, but generally anything here or above is considered as inefficient. So that's all I wanted to cover in today's lecture. Thank you.